second lecture.
Thanks. So, thanks to all of you for coming back. So today we are going to talk about lattice gauge theories, which are these discrete versions of quantum Yang-Mills theories. So these were proposed by Wilson in 1974. The famous, basically the same guy who discovered renormalization group. So let's define lattice gauge theories in arbitrary dimensions. So earlier we were discussing quantum Yang-Mills theories in dimension 4, but now we'll go to arbitrary dimension D, and 2 and higher. And as before, let G be a matrix Lie group containing UN for some n. So it's a subgroup of unitary matrices. And we define these theories first on finite subsets of the lattice. Okay. So we take the lattice and we define the theories on finite subsets. And here is the space of configuration. So you take this lambda, the subset of the lattice, and for any two adjacent vertices, you attach a group element to that edge called uxy. And for the reverse edge, you put uyx to be uxy inverse. So you have a unitary matrix along in one direction. In the opposite direction, you have the inverse of that matrix. Okay. And let G lambda denote the set of all such configurations. Okay, just for convenience, we give it a name. Now here is an important definition. A square bounded by 4 edges is called a plaquette. So it doesn't matter what dimension, it's always just a square bounded by 4 edges. That's a plaquette. And let's say you take a plaquette P, and let's say you have vertices x1, x2, x3, x4 in anticlockwise order, where you define anticlockwise in some appropriate way. And then suppose you're given a configuration of matrices attached to edges. You define the matrix attached to this plaquette P as a product of the matrices along the edges, so in the right direction. So you go from x1, x2, x2, x3, x3, x4, and back x4, x1. So you multiply the matrices, and then you get the matrix attached to a plaquette. Okay. The Wilson action of this configuration U is then defined as follows. It's the sum over all plaquettes in this set lambda. The real part of the trace of I minus UP. Okay, that's the Wilson action. I is the identity matrix. And more generally in physics, what they do is they have reason for doing this. That instead of UP, you substitute rho of UP, where rho is some representation of G. So you can get a larger matrix or a matrix of large dimension or matrix of smaller dimension, So, but we'll not worry about that. We'll just take this definition. Okay. And the reason why they need to take these representations is that for example, suppose you're considering the strong force. So the strong force is SU3. So it's a 3x3 matrix. But sometimes it has to interact with matter fields which are represented by, let's say, vectors of length 4. So how can a 3x3 matrix interact with the vector of length 4? So you have to take a 4-dimensional representation. And so that's why they have to work with more general representations. Okay. So now let sigma lambda be the product Haar measure on this group. And then you define a new probability measure on this space of configurations as follows. So you take a configuration U, you take e to the minus beta times the Wilson action of U, and you put this density in front of the product Haar measure, and then you multiply by some appropriate normalizing constant that gives you a probability measure. So this is called lattice gauge theory on this set lambda.
A question
Yes.
So I presume it doesn't matter how we choose the plaquettes for each.
It doesn't matter. So it has to be some consistent way. So since we are taking the trace, it doesn't matter what's the starting point. And also, since we are taking the real part of trace of I minus UP, it will not matter whether you take it in this way or in this way. So somehow.
But I mean, if you choose with one single vertex, there's obviously multiple plaquettes that you could choose.
Yeah. So
I guess doesn't matter because that just means that it just permutes the.
Yeah. Yes. So there'll be, for instance, in 3D there will be plaquettes like this or like this or like this. So you have to sum over all possible plaquettes, and and for each square you have to just choose one direction in which you'll take the product of those matrices.
And so is it essential that we're working on a graph of, like something on ZD? We can't do it on like triangles or.
So for the triangular, if you want to do something like a different lattice, then you have to. I'm sure you can do it. You have to appropriately figure out what the suitable action should be. So we'll see where this action is coming from. So why is this action defined in this way? What is its connection with the angle theory? And that will indicate how you should define it for a different lattice if you want to. Okay.
You don't just define it the same way. It's just different choice of plaquettes.
Maybe you'll have to multiply by some things. I didn't think about that, so I don't know. So this probability measure is called lattice gauge theory on this set lambda. So the theory in physics means model. So on a gauge group or with gauge group G with inverse coupling strength beta. Okay. So is the model more or less clear? So it's a model on a space of configurations. It's a probability measure on a space of configurations where the configurations consist of matrices attached to unitary matrices that attach to edges. And with the restriction that if you just reverse an edge, the matrix gets inverted. That's it. There's no other restriction. And then you have the product Haar measure on these matrices. So you take the product Haar measure and put a density in front, and the density is e to the minus beta times the Wilson action, where the Wilson action is defined as in the previous slide. You sum over all plaquettes that you have, and for each plaquette you take the product of the matrices, you take I minus that, the trace, real part of that, sum over all plaquettes, and that's the lattice gauge theory. Yes.
Just to have a picture, what does it favor? What we should think, like the gravitate and things like that?
Yes. So that's a good question. So suppose beta is large. Okay. Suppose beta is large, then what happens is that it will try to make this thing small. Okay. So this thing small. So you see, this is a unitary matrix. So its eigenvalues are all on the circle, right? And so when you add them up, when you take the trace, the sum of the eigenvalues, it's always less than trace of the identity. The trace of the identity is just n. So it's trying to make it as close to the identity as possible. So it's trying to make these plaquettes, so the products of the matrices along these four edges, as close to the identity as possible if beta becomes larger. So that's what it's trying to do. So this is minimized, this action is minimized when every UP equals the identity. And that's not a unique configuration, so there are many configurations like that. But it's trying to make, so in the continuum terminology, so it will become more clear as we make the connection to the continuum. It's basically trying to reduce the curvature of the connection. So these matrices, okay, so what do these matrices do? They're like a discrete connection, which means the following. So suppose you have a single group element at a vertex. As you move along a path, you multiply this group element by the elements that you get along the edges of the path. So it's like a transport. It's like you have a single group element and then you're transporting it. Okay, and so if these plaquettes are all identity, what will happen is that you will get back the same element as you go around a closed path. Okay, so that's zero curvature. There is no curvature. And when you have curvature, you get back something else as you go around a closed path. Okay, so it's trying to minimize the curvature. So this is with a finite set lambda, and then sorry, this should be ZD. There's an infinite you can consider infinite volume limit. So what you do is usually the usual thing that you do in statistical physics. So you have a theory on a finite set, and then you define everything arbitrarily outside that set. And then by compactness, you can say that as the set grows, you can have weak limits of these measures. Okay.
Are the minimizers sort of homogeneous or translation invariant, or are they staggered, or do they?
So we'll see what the minimizers are soon. So these are basically, everything that you can get by gauge transforming the identity. Yeah. So we'll come to that. So this infinite volume limit may or may not be unique. So this is a big question in statistical mechanics. Always, whenever you have this kind of a statistical mechanical model, whether this infinite volume limit is unique or not. And this is actually an open problem. So in dimension 4, actually also, I think in dimension 3 also, it's not really known whether these infinite volume limits are unique. Okay. So I think they're believed to be unique, but it's not known. I mean, it's certainly unique for small beta. For when beta is small, there are standard arguments in a Dobrushin condition. You can look up Dobrushin condition if you're not familiar with it. You can prove that for when beta is small, you have unique weak limits. But the question is when beta is large, and it's believed, I think, that the limits that the infinite volume limit, there is no transition. The infinite volume limit is unique. Okay, so now we'll see where this theory is coming from. What is the connection between these discrete theories and the continuum limit? So before that, we'll need so of course, we don't know rigorously how to prove the existence of the convergence to the scaling limit, but the heuristic argument that Wilson gave. So roughly speaking, I'll outline that. So recall the Baker-Campbell-Hausdorff formula for products of matrix exponentials. So you have e to the b times e to the c. If b and c are two matrices, is e to the b plus c plus half times the commutator plus higher commutator. So, okay, that's the. And then you iterate that. If you have finitely many matrices, you get the product of the exponentials is e to the sum plus half times the sum of the commutators plus higher order terms. Suppose that these are skew Hermitian matrices. Then the commutator of any two skew Hermitian matrices is also skew Hermitian. Okay, so this whole thing up here is skew Hermitian. Okay, and skew Hermitian matrices have imaginary eigenvalues, so the trace of that is imaginary. So when you take the trace of such a thing, you have first you have 1, then you have the trace of this part, then you have the trace of this thing squared. Now the trace of this thing is imaginary, so when you take the real part of that, the first term goes away. So here is what you get. So suppose the matrices are of order epsilon, the entries are of order epsilon, some small epsilon, and when you add them up, it's of order epsilon squared. So when you add them up, there is some cancellation and it's even smaller. Then when you take the real part of the trace of I minus this product, you get this. So why the square over here? The square is because the first term, when you do this expansion, when you take this side and you expand it, the first term has a purely imaginary trace. So when you take the real part of that, that goes away. So only the square survives, and then there are higher order terms. And you can, this epsilon to the 5, you can check. It needs a little computation using these conditions, but you can do that. And so this is what you end up with. So when you take the real part of the trace of I minus a product of matrix exponentials like this, under these conditions, that the matrix entries are of order epsilon and the matrix entries of the sum are of order epsilon squared. Any questions about this? So you see, the critical thing is that you have the square, because the first term has, the first term in its expansion is purely imaginary trace, and so therefore when you take the real part, that goes away, so you're left with just the second term. Okay. Right. Okay, so you have this formula now. Now let's, so we'll use this. So we will. So remember this formula, we will use it soon. So recall this discretization of the Brownian bridge that we discussed before. So it'll go along the same line. So just as in that problem, you discretize r to the d as epsilon z to the d for some small epsilon. Take some smooth connection form A on r to the d, which means that this is a smooth map from R to the D into the Lie algebra to the power D. Okay. Let E1 to ED be the standard basis vectors. And then you do the following. You convert this connection form into a bunch of matrices as unitary matrices as follows. So to each edge of the scaled lattice, sorry, this again should be D. Each edge of the scaled lattice, define the unitary matrix attached to that edge as e to the epsilon times aj of x. And then you, for the opposite edge, it's just the inverse matrix. Okay. So yeah, I'm starting with this connection form. So the goal is the following. I'm starting with the connection form. I'm converting everything to the scaled lattice. And what I want to show is that the Wilson action reduces to an approximation of the Yang-Mills action if we take the Wilson action as defined by Wilson. Is this okay? All right. So this defines a configuration of unitary matrices assigned to directed edges of epsilon z to the, sorry, d. I changed n to d. I forgot to change in various places. Okay. So now take a plaquette. Okay. So a plaquette is as follows. You have 4 vertices x1, x2, x3, x4. And so this must be of this form. x1 is x. x2 is x plus epsilon ej for some j. So there are 2 j and k. x3 is epsilon x plus epsilon ej plus epsilon ek. And x4 is x plus epsilon ek. So you go like this. Okay. So let P be the plaquette formed by these vertices. Now let UP be the product of these matrices. Okay. E to the epsilon aj of x1 because it's going in direction j. This is ak of x2 because it's going up in direction k, and this is minus aj of x4 because it is going back in direction j, and this is going down in direction k. Okay, so maybe I should draw a picture. Plaquette. This is x1, x2, x3, x4. So x2 is x. So x1 is x. x2 is x plus epsilon ej. x3 is x plus epsilon ej plus epsilon ek. And x4 is x plus epsilon ek. Okay. So you're going around like this. So now we intend to apply the Baker-Campbell-Hausdorff formula, but before that we have to do a little bit of processing, which is you have this x1, x2, x4 and x1 here. Now x4 and x2 are different from x1, so we just do a little Taylor expansion. So ak of x2 is ak of x plus epsilon ej, so that's ak of x plus epsilon times del ak del xj. So when you take the sum of these 4 things, which is the first term appearing in the formula, you get this del ak del xj minus del aj del xk times epsilon plus order epsilon squared. Yes.
What was the subscript on the A again? The first one?
Which one?
How was A was the UP was the U's were defined as these. How do you get the subscript J or K?
Oh, yeah. So here. So when you're moving in direction j, you put e to the epsilon aj. So remember, A has 4 components: A1, A2, A3, A4. Okay. So when you have an edge going in direction j, you put e to the epsilon aj. When you are going in direction k, you put e to the epsilon ak. Okay. So that's how these you convert these connection form these Lie algebra elements. You use them to get these matrices. Okay, that's a good question. Okay, so you clearly see the first term in the sum of these things. When you do this infinitesimal expansions, you get this form, which is the first term that appears in the curvature form. Okay. And then you recall this formula. So sorry, I'm going back to this this formula here. So you have this formula. Real part of trace of I minus product of matrix exponentials is trace of this sum plus the sum of the commutators squared, half the commutators. So when you substitute this back here, you get this. Okay. So anyway, even if you haven't followed all the steps, so this is what you get at the end. Is that so? That's the general thing that you start with the smooth connection form A, which has D components A1, A2, AD, and use that connection form to assign matrices to little edges of a rescaled lattice using just matrix exponentials. And when you take the real part of the trace of I minus UP for a little plaquette, you get basically you recovered the trace of FJ x squared. So you recovered the curvature form. So it's a discrete way of recovering the curvature form. And then when you sum them all up and basically you have to divide and multiply by epsilon to the d since you are trying to mimic the integral. So this is what it reduces to. So this is Wilson's heuristic that the Yang-Mills action, the Wilson action is approximately epsilon to the 4 minus the dimension over 4 times the Yang-Mills action of this original connection. So if you start with a smooth connection, you get this relation. Okay. So so you see the connections that you expect to get in Yang-Mills series are not smooth, very far from smooth, but it's kind of the same heuristic that led to the definition of the Gaussian free field, for instance, using the discrete Gaussian free field, because in the physics definition of the Gaussian free field, you have the density e to the minus integral gradient f squared, and gradient f squared is approximated by the discrete gradient for smooth functions, certainly not for the Gaussian free field kind of functions. So, but it's still in some way it makes sense. Yeah, so then Wilson said that you should scale. So what you should do is that to define a Euclidean Yang-Mills theory, you have to define a lattice gauge theory on a scaled lattice, on a lattice of with epsilon, and then as epsilon goes to 0, you have to scale the inverse coupling strength beta like epsilon to the 4 minus dimension. Okay, and that was Wilson's prescription for constructing Yang-Mills theories, Euclidean Yang-Mills theories. So now here is a remark that the most important case is dimension 4, but you see beta does not scale at all with epsilon when dimension is 4 because it's epsilon to the 4 minus d. So now I don't know for what reason, but they keep saying that in dimension 4 beta should scale like log of 1 over epsilon, so log epsilon. That's not like a constant as Wilson originally said. And I've heard at least one dissenting person. Somebody said that no, he doesn't believe that. He still believes that Wilson's original. So it's not clear, but this is the most commonly held belief that beta should scale like log 1 over epsilon in 4 dimensions. Okay.
When you say should scale, you mean should scale that way in order to what?
In order to get some kind of non-trivial limit.
And a limit for what?
For the lattice gauge theory, yeah. For the
single loop, for the law of a
yeah. That's not clear. So yeah. So what I think what the physics mean is that what they mean is that a non-trivial limit of correlation functions. So if you take a plaquette, if you take another plaquette at some distance, okay, fixed distance, as epsilon goes to 0, the distance between the plaquettes, the Euclidean distance should remain fixed. Okay, and then the correlation between these two variables, the real part of the trace of one plaquette and the real part of the trace of the other plaquette, the correlation should go to some non-zero limit. I don't know. Yes, Antti, you have.
This log 1 over epsilon, that was the Nobel Prize 2002.
Okay.
And it's called asymptotic freedom. And it follows from renormalization group analysis of that.
I see.
So that's the only thing which is sort of on the verge of being rigorous.
So I thought the renormalization group you cannot go below a certain.
No, you can go towards when the thing becomes free, namely when you go towards the Gaussian theory.
Okay.
So that's the short distance behavior. But when you go towards high temperatures, then it's difficult.
Okay.
You repeating one unit here.
Oh, what Antti was saying is that this log 1 over epsilon got a Nobel Prize in 2002. And
what exactly got? Is the Nobel Prize just that if you don't have a log epsilon, then you get a limit where?
Yeah, that's the way you have to scale it in order to get the limit. The scaling limit is.
Or did they actually prove that log 1 over
Oh,
epsilon
they
is
just
the right way, or
they
they
did
showed the
a
constant doesn't?
perturbative calculation, but that's sort of believable because everything is weakly coupled in that limit. But in these theories, the continuum limit is supposed to be quite simple compared to the long distance limit, which is the quark confinement.
Sorry to be asking you questions, but could you say in a sentence, like, what was the mathematical content behind this Nobel Prize?
What is the mathematical content? No, this is a physical calculation.
Okay, what's the mathematical statement?
It's a calculation of the beta function, if you know what that is. So you can define sort of the strength of the interaction of the nonlinearity depending on scale. Okay, and once you vary the scale, there is a function which describes that. That's called the beta function. And these people who got the Nobel Prize computed the beta function, and the consequence of that calculation is this behavior of the what people call the bare coupling constant as a function of the lattice spacing. So this is sort of something which is highly likely to be true. Let's put it like that.
So you see, from this conversation, you get a taste of the challenges that I've faced while, coming to this point, presenting.
Who is the person saying that it is constant?
Oh, Erhard Zeiler, so of Osterwolder and Zeiler is. Okay. So, okay. Okay, so there are other actions. The Wilson action is not the only action that occurs in literature. Essentially, any action that is gauge invariant, so I'll discuss what this means in the context of lattice gauge theories, and heuristically scales to the Yang-Mills action as the lattice spacing goes to 0 is acceptable. That's my understanding of the situation, that you can consider other actions also. Actually, I'm not even sure how important gauge invariant is as long as you have this, but let's do gauge invariant. So notice that the Wilson action can be represented as the product over plaquettes of f beta of up, where f beta of up is e to the minus beta times the real part of the trace of I minus up. So this basically is a measure of how far this matrix is away from the identity. Okay, so f beta. So if beta is large, then this is like a bump function which goes down very quickly away from the identity, and if beta is small, it goes down smoothly away from the identity. But it's basically a measure of how far up is from the identity. So you can replace it by some other functions. For instance, an alternative is this heat kernel action, where f beta is replaced by rho t, where rho t is, suppose you have a Brownian motion on the group, and you start from the identity, and you look at its density at time t. Okay, so if t is small, it's very concentrated near the identity. So this, if you just replace this by rho t, where you have to take t to be 1 over beta, it will give you a valid action. So this is a heat kernel action. And in the specific case of G equals U1, this heat kernel action has an explicit form. It's known as a Villian action. Okay.
So in principle, there's no reason, you could take something else than where instead of taking just the product, ordered product of the thing, something involving like free.
Yeah, you can take other things. You can take other things. Any function of up will be gauge invariant, and you can take other things as long as I think anything reasonable should give you the Yang-Mills action in the limit. So, yeah. Okay. So this is actually has proved to be much more useful in many many papers, especially for U1. This villain action. So we'll discuss that. Okay, so the next thing is Wilson loops in lattice gauge theories. So these are also much easier to define than in the continuum setting. So suppose you have a lattice gauge theory with gauge group G, and then you take a closed loop gamma with directed edges E1, E2, En in some order. Okay, it doesn't matter where you start from. The Wilson loop variable W gamma is defined as a trace of U E1, U E2 up to U EM. You have to take the product. And so since this is a trace, it doesn't matter where you start from. It matters in which order you take, but it doesn't matter where you start from. So, and sometimes you take the real part of this trace. So both of these are called Wilson loop variables. Okay, either you take the real part of the trace or just the trace. Doesn't matter so much. So we have discussed earlier that why this is a discrete approximation of Wilson loop in continuum theories. So we saw this derivation or this definition in terms of this. Okay. So these are the observables. So here is the area law for lattice gauge theories. So it is believed that for large class of non-abelian theories, for instance SU3, 4-dimensional lattice gauge theory satisfies Wilson's area law. So which means that for any nice enough loop, gamma, the Wilson loop expectation, so the expected value of this Wilson loop variable under the lattice gauge theory is bounded by essentially e to the minus the area of gamma, where the area gamma is the minimum surface area enclosed by gamma. So now gamma is a loop in the lattice, so you have to define minimal surface area in some appropriate way, but this is what it is. And so this is a well-posed mathematical problem. Okay, the lattice gauge theory that I just stated is a completely well-defined probabilistic theory, and this question is a well-posed question, but it has not been proved except in 2 dimensions and a few other cases. So this would be a big breakthrough to prove this even for rectangles. I don't think it has been proved in any example in 4 dimensions. Okay. So in 4 dimensions, even if you can prove this for rectangles, that would be enough somehow.
Why should this be true?
This is expected to be true, but one. Okay, so first of all, so we'll see in some cases. So in small enough beta, this has been proved. So that's one thing. That's in small enough beta, it's been proved, and then. What is generally thought, as Antti was just saying, that you can go from large beta to small beta by doing renormalization. So as you do renormalization steps, lattice gauge theories, the beta keeps decreasing. So somehow that's why they believe that small beta behavior. Anyway,
isn't it proven in for small beta?
Small beta, yeah, I'm coming to that.
In 4 dimensions also.
Yeah, in any dimension. Yeah. In any dimension. So the Osterwalder-Zeiler theorem is that when beta is small, the area law was rigorously proved in any dimension for essentially any gauge group. Okay, so beta is small enough, this always holds. And
small
if
means that the effective beta is scaling with the grid size.
No, here I'm just taking fixed grid, so ZD. Okay, just Z to D. Take a lattice gauge theory on ZD, so it takes any weak limit of lattice gauge theory, infinite volume limit of lattice gauge theory.
Fixing beta and letting the rectangle get larger.
Yeah. So what I'm saying is that there are constants C1 and C2 just depending on the dimension and the beta and the gauge group, so that this holds for all gamma.
Right. But the point is, if you wanted to get a scaling limit, you wouldn't be fixing beta and scaling it. You would be letting
beta grow. Yes.
As you change.
Yes. So now, unfortunately, this is not sufficient for quark confinement. So if you remember, quark confinement, proving quark confinement was the original goal of the area law. So to prove this, one has to at least show that this area law holds for all large enough beta. So it doesn't suffice to prove it's for small beta. Yeah, so more accurately, one has to show this area law should hold in the continuum limit, which involves taking beta to infinity, which is what Scott was just saying. And moreover, it is not supposed to hold in 4-dimensional U1 gauge theory, or in general in 4-dimensional abelian gauge theories. So for instance, U1 gauge theory is about electromagnetism, and electromagnetic fields do not confine matter. So that's the physical reason why this should not hold in 4 dimensions. So however, the Osterwalder-Zeiler theorem implies that this area law holds, for small beta, even for 4-dimensional U1 lattice gauge theory. So what can be the only conclusion from that? The only conclusion is that these strongly coupled theories, that is small beta, does not represent physical reality. Okay, so you have to go to the large beta regime to make physical conclusions.
For U1, it's not proof that it doesn't hold?
Yeah, it is proved for large beta. So that's the next slide. Okay. Any questions about this slide? So this proof uses representation theory and high temperature expansions, but I don't have time, so I have a simple proof of that, quite elementary proof of this result, that it holds for small beta. Okay. Now the area law at small beta for 4D U1 lattice gauge theory. So this was quite confusing to people for a while. That on the one hand you shouldn't have confinement in abelian in U1 theory in 4 dimensions. On the other hand, the area law was proved. So Alan Guth in 1980 proved that this area law does not hold at large beta. Well, it's a physics argument, but it's close to being rigorous. That it does not hold at large beta in 4-dimensional theory, and a fully rigorous proof was given by Froelich and Spencer for 4-dimensional U1 lattice gauge theory with the Willian action. Okay. So they showed that when beta is large, you actually have this lower bound, that the Wilson loop expectation is lower bounded by e to the minus the perimeter of the loop. Okay. So in somehow this perimeter law seems more reasonable, right? So you're multiplying things along a loop, so you're multiplying the number of things that you're multiplying is the perimeter of the loop, so you expect to get something like e to the minus the perimeter, and it's a little bit mysterious, why you expect to get something like e to the minus area in many cases, and why you have that in high temperature.
So that's for rectangular.
So this one, I think it was for rectangular loops. So they didn't go for the generality. I mean, the proof is quite complicated as such, so that I don't think they went for the generality. So it's only for rectangular loops. So this implies in particular, if you remember from the previous lecture, that is quark-antiquark potential VR. If you have a quark-antiquark pair at distance r, the potential energy between them remains bounded as r tends to infinity. So this perimeter law implies that it remains bounded, and hence it resolves this issue that quarks need not be confined in electromagnetic theory. So this is known as deconfinement transition of 4-dimensional U1 lattice gauge theory. Yes.
So what is it? The phase transition is where beta small you have
area law.
Exponential in the area, and then you have the critical value, and above it's exponential in the perimeter.
I don't think the existence of any critical value was proved. So it's just for small enough beta you have area law, for large enough beta you have perimeter law. That's all that was proved.
But it's expected.
I think it's natural to expect that there will be a phase transition, but I don't think any such result exists. Yes.
You said it's confinement of matter, but is there like a simple interpretation of what it means? Because here you only introduce the gauge field, but no matter field. So how do you relate this?
Yeah.
To some.
Yeah, I don't know about the I don't know about the physics. The proofs are the small beta areal, as I said, you can prove it not much difficulty. You can so the original proof uses this representation theory, but I have a simple proof of that. But this one I don't have a simple proof. This is a difficult theorem. So I. Yeah, I don't have a simple proof of that. Well, we can try, but so there are, the third big theorem in this area is this Goffert-Mack theorem. The question is 4 dimensions really important for understanding confinement? So is it something special that's going on in 4 dimensions? So indeed, that is the case. So what Goffert and Mack showed is that in 3 dimensions, so in 2 dimensions, area law holds for anything at all beta, essentially. So you can, in 2 dimensions, none of this matters. So so you have area law for any group at any beta. So in 3 dimensions, Goffert and Mack showed that even U1 gauge theory with Willen action satisfies the area law at all beta, or at least at all large enough beta. I don't remember exactly whether they proved for all beta for all large enough beta, but more or less the same. So this if our world was 2-dimensional, even light would confine matter. So light would be electromagnetism. So okay. So the U1 theory has no deconfinement transition in 3D. So one point is, why are they all using Willen action?
5D would be okay.
What?
5D would be okay.
5D. I don't know of any results in 5D for this line of work. Yeah, I don't know about
it. Should be easier, right? Anyway.
Possibly. I don't know. So it's very specialized, actually. So I'll tell you in a minute, what this involves. So this Froelich-Spencer proof, as well as this Goffert-Mack proof, uses the Willen action because of mathematical convenience. And what is that convenience? The convenience is that this U1 gauge theory with Willen action is dual. You can have a Kramer-Wannier type duality that you have for the Ising model. You can have a similar duality for these models. So for instance, 4-dimensional U1 gauge theory is dual to itself, I think. No, it's not itself. So you, okay. So 3 dimensions, if I remember clearly. So 3-dimensional theory is dual to the Z ferromagnet. So which is basically the Gaussian free field, but where the values of the field are integer valued instead of continuous valued. So that is the dual of this theory. So you can have this duality relations using this character expansion for abelian groups. Not only for U1, for any abelian group you can do this. You can, So basically, you remember you had this. The density was a product of f beta of UP. Okay. Now f beta is a function on the group. So you can substitute the character expansion of that function, and then you extract the duality from that. Okay. So for abelian theories, you can get these dual theories, which convert large beta to small beta problems. So it's just like you have a very sharply peaked function. You take the Fourier transform, it becomes flat. So it's the same thing. So you have a large beta problem, which is a kind of sharply peaked thing, and then you take the dual theory, it becomes kind of flat. So that's what these papers use. The Goffert-Mack paper, the Froelich-Spencer paper, they all use that. And this is in 4 dimensions, it becomes a little more complicated because you cannot imagine 4 dimensions. So you have to use this exterior calculus to go to the dual theory. So okay. So this trick, unfortunately, this is only available for abelian theories. So there has been attempts to do non-abelian duality, but I don't know of anything that has proved useful till now. So this doesn't work. So you can have a look at these papers to see exactly what the dualities are, but so we'll not discuss this because it doesn't seem to work for non-abelian theories. But maybe there is a way. So you can replace the character expansion by the corresponding representation theoretic expansion, but that doesn't seem to work. It becomes extraordinarily complex. Okay. gauge transforms from a lattice gauge theory. So gauge transforms are simple to describe. So what you do is, suppose that you have a lattice gauge theory and a gauge configuration U. A gauge transform is induced by just a map from the vertex set into G. Okay, so you have a group element on each vertex, and this is what it is. Very simply, this is just you take any group element attached to an edge, you pre and post multiply it by the vertex elements, like this. So U prime xy is hy u xy hx inverse. And these are gauge equivalent, so this is clearly an equivalence relation, because if you just apply H inverse to U prime, you get back U. And then you can check that this corresponds to what I wrote down for the continuum version. And then you, as usual, you say a function is gauge invariant if f is the same on all gauge equivalent configurations. And you can check that the Wilson action, heat kernel action, the Wilson loop variables, these are all gauge invariant. Well, gauge fixing, this is another important thing, and this is much easier in lattice gauge theories. So there is a general prescription for gauge fixing to choose one from each equivalence class. So basically this answers a question that was raised previously, is that what are the set of all minimizers is basically everything that's gauge equivalent to the identity configuration. So you can take the configuration that's equal to the identity everywhere, and a configuration minimizes the Yang-Mills, the Wilson action if and only if it's a gauge equivalent to the identity. So there's this general prescription, which is you take any rooted spanning tree of the set and a gauge configuration U, and then you define your H as follows. If R is the root, you define HR to be the identity, and then you inductively define H at each vertex, each node of the tree, as you take its parent X and define HY as HY U XY HX inverse to be identity. So you basically make all the group elements equal to the identity on the tree. Okay, and since this is a tree, this is well defined. And let U prime be the gauge transform of U by H, so that U prime is a configuration which is identity on all edges of the spanning tree. And you can show that for any fixed spanning tree, this process is a map from the set of configurations into the set of equivalence classes. So if two configurations are gauge equivalent, then they will produce the same U prime. Okay, so this is gauge fixing, and there are various choices of spanning trees that produce different results, but any spanning tree will give you a gauge fixing procedure. So it's also easy to show that these gauge equivalence classes all have exactly the same size because of the symmetry. So you don't need these procedures. Okay. Let me tell you a little bit about two-dimensional theories, because there is a lot of math about that. So suppose lambda is a rectangle in Z2. Let T be choose this specific spanning tree, which consists of all horizontal edges and all vertical edges on the left boundary. So that's the spanning tree. So you take a rectangle, and then you take the left boundary, and you take all horizontal edges. That's the spanning tree, and you take the bottom left vertex to be the root, arbitrarily choose some root. And then you do gauge fixing. So what this does is that it makes the matrices on all horizontal edges and everything on the left boundary to be equal to identity, gauge fixing. So a gauge equivalence class can be represented by any configuration. So any configuration which has identity on all these edges is a represents a gauge equivalence class, and these are distinct equivalence classes. And since these have all the same size, the probability density on this reduced space of configurations is the same as the original one. So instead of the original model, you can consider the model where you have this rectangle, and all the matrices attached to the horizontal edges and the left leftmost left boundary there, these are all identity, and the rest are free to be whatever they choose to be. And then you put the same probability density, and that gives you an equivalent model. Okay. So what I mean by equivalent model is that if you take any gauge invariant observable, such as a Wilson loop variable, the expected value is the same in this new model as in the old one. Okay, so in this gauge fixed configuration, only the vertical edges, except the leftmost ones, are not equal to identity. So these edges can be classified according to height. So there's different layers of vertical edges. So at each height n, you have a layer of edges. So you enumerate these edges as en1, en2, etc. And you can check that the probability density of this whole configuration is just this. You take product over n, and then for each n, you product over I, e to the minus beta real part of trace of I minus u ni plus 1 times u ni inverse. And that's because, you see, when you have these four plaquette like this, these are fixed to be identity. So when you take the plaquette variable, it's just this times this inverse, because these are identity. Okay. So this is okay. So even if you don't see this immediately, but just take my word for it. This is the probability density, the joint density of this gauge fixed configuration, and this is very simple. So this shows that first of all, for every n, the sequence un, u1, un, e2, so that these matrices that you get on the vertical edges at a level, this is a random walk with IID increments on the group. Okay, this is a random walk on the group with IID steps. And for various levels, these walks are independent of each other. Okay. So this observation, this makes 2D theories very amenable, to probabilistic analysis. So proving area law, continuum limit, etc. So there is a whole body of literature on that by many authors, starting with Len Gross, I think, and many others. Okay. And then you can also do things like stochastic calculus, etc. So all kinds of things you can use for 2D. And it can get much more interesting if one considers 2D theory on closed surfaces instead of R2. In that case, the gauge fixing is not as simple, because things come back on themselves. So it becomes more challenging. However, the 2D methods do not extend to 3 and higher dimensions. So in particular, this decomposition in random walks that you have in 2 dimensions, it just doesn't work if you go to 3 or higher dimensions. Okay, but it's a good example of what you can do with gauge fixing. So it's a good demonstration of the idea of gauge fixing. Okay, so what do you do in higher dimensions? So mostly it's open other than these results. So these are the main results that are available: Osterwalder-Zeiler, the Guth, Froelich, Spencer, and the Goffert-Mack results that you have. And the main problems are prove the area law at large beta, or prove decay of correlations at large beta. So exponential decay would be what people really want to show, but I don't think any decay has been proved at large beta. Construct the continuum limit. So there is this long series of papers by Balaban, 13 or 14 papers written over a span of 7 or 8 years in the 80s. So this is based on its framework of constructive field theory. But however, Balaban's work is mostly about understanding the partition function. I mean, first of all, I haven't been able to read it, but it's really challenging. But there are many people here who may be able to actually recover what Balaban was doing, because there is no kind of compact survey of that work. It's just these long series of papers, long series of long papers. Okay, not short papers. So now what Balaban was mainly studying is the partition function. It's not clear what the limit object is, even if this whole work is understood somehow. It's not clear what the limit object is, and also calculations like how to calculate Wilson loop expectations or any other observables in the limit. So that's not clear. So I have more details in this survey. Now there is a set of recursive equations for Wilson loops.
Your paragraph doesn't say anything about what Balaban actually did.
No. No. I would need many more lectures for that. So I'm time limited. Well, I can tell you a little bit. So So basically, it's about this renormalization. So you have this original, lattice gauge theory, and you renormalize into a coarser lattice. Okay, so you take a coarser lattice. How do you define the group element attached to the edge of the coarser lattice? It's not just multiplying the product, multiplying the edges. So there is a more complicated, there are more complicated schemes of doing this renormalization. So you take a whole bunch of paths from one point to the other, and then you somehow average over them. So if you just average matrices, you don't get a group element. So you have to do it in some other way, to take an average and get back a group element. And then what Balaban is doing is he's taking this epsilon lattice, and he's scaling it back. So let's say 2 epsilon and 4 epsilon, 8 epsilon. He's scaling it back, and you're getting it to a macroscopic lattice. And if you start from this epsilon lattice and you go to this macroscopic lattice, you get some probability measure. And that is showing that this collection of probability measures is compact in some appropriate space, so that there is a scaling limit. So that's more or less what the idea is, but it's
so there is a continuum object somehow constructed this way.
I didn't see that stated clearly, so that's not, it's not, well, we can discuss this. It's not. Okay, so the only thing that I know that holds for general dimension is the set of recursive equations for Wilson loops. So this is what we'll discuss tomorrow, which is this master loop equations and gauge string duality. So I haven't spoken anything about my work yet, so this will involve some of that. I hope to start this a little bit today, but I don't think there is time. So we'll see these next time. Okay, thank you.
Questions? Comments?
Thank you.